We typically only find this enigmatic unit of physics in the center of black holes. But what if these singularities don't exist? A scientist has now demonstrated that the notion of a singularity may be incorrect, which would imply that our universe may not have begun with a Big Bang. According to theory, a singularity is a point at which something is simultaneously infinitely small and dense. This phenomenon is most likely found in the center of black holes, where gravity is so strong that nothing can escape, not even light, and the known laws of physics cease to function. In theory, there was also a singularity at the beginning of the universe, when all matter and energy were concentrated in a single, minuscule location. But the worst part is that what if there are no singularities? Renowned scientist Roy Kerr, who is an expert in black holes and was the first to characterize the gravitational field of revolving black holes, has questions about the theory, and for good cause. Kerr discovered the Kerr metric, among other things. What is the origin of the concept of singularities? Have you ever questioned how scientists arrive at these conclusions? The Big Bang, the interior of black holes, and much more. Since no one or anything can enter a black hole, and none of us saw the universe's inception, how do scientists know this? Albert Einstein's general theory of relativity, which was published in 1915, gave rise to the concept of the singularity. In it, Einstein explains how masses bend space-time and produce gravity in the process. The Schwarzschild solution, which characterizes the gravitational field of a non-rotating spherical M, is among the first solutions to Einstein's field equations. Object of mass Carl Schwarz's child found that such a body may have a boundary and an event horizon. A singularity, a point of infinite density and gravity where the known rules of physics break down, is located at the center of this solution, beyond which nothing, not even light, can escape. Thus, in the 1920s, Schwarzschild described a black hole without being aware that such objects ever existed. Therefore, the singularity was determined only by mathematics and existed before to the discovery of objects that closely like this description. Nevertheless, we might have been mistaken, and black holes are something entirely else. In 1965, Roger Penrose analytically demonstrated that singularities are a necessary component of general relativity. If the event horizon is real, then singularities must unavoidably exist in black holes. Scientists paired a visible phenomenon with a mathematical conclusion if they have an event horizon, which allows us to view a black hole's event horizon differently from its inside. The border is the event horizon. There is a slight catch to this theory, though, because stuff is so close to the black hole that no known force could pull it away. Stephen Hawking demonstrated that a tiny quantity of radiation emanates from black holes, indicating that the event horizon is not absolute. In 2020, Roger Penrose received the Nobel Prize for a study that addressed the singularity once more. In that publication, he demonstrated that space-time is so heavily warped near a singularity that the conventional rules of physics no longer apply. A fundamental contradiction between general relativity and quantum mechanics is highlighted by Penrose's singularity theorem, which is based on the idea of geodesic incompleteness. It states that the paths of particles and light rays, known as geodesics, must end in a black hole. This suggests that space-time itself ends at these points, leading to the idea that singularities are real. Despite the fact that general relativity predicts singularities that are points of infinite density and gravity, quantum mechanics fails at these scales because it does not permit such infinities. This contradiction demonstrates once more that there is a flaw in our physical disciplines that we have not yet discovered. General relativity and quantum physics are inextricably linked, and both describe our world. As Roy Kerr's most recent research indicates, if singularities do not exist, the ramifications could be significant. Kerr effectively demonstrates that Penrose's findings might be incorrect and that rotating black holes have ring-like structures rather than point singularities or no singularity at all. This finding could indicate that spacetime does not terminate inside black holes. If Kerr's theories are accurate, then singularities are not necessary for the general theory of relativity to function. This might resolve the conflict with quantum mechanics and give our physics entirely new dimensions. Since black holes are among the most enigmatic objects in the universe and most likely combine incredible powers, they are once again being hailed as the key to a thorough understanding of the universe. What does the Kerr metric say? It's amazing how much these mysterious black phenomena challenge our scientists today. In 1963, the Kerr metric was created as an extension of the Schwarzschild solution. Kerr focused on revolving black holes, whereas Schwarzschild studied non-rotating spherical black holes geometrically. This is a significant difference. The majority of black holes known to astronomy rotate, but not all of them do, and not all of them have the same shape, according to his research. In addition to a ring-shaped singularity, Kerr described a black hole with two horizons, the inner Cauchy horizon and the outer event horizon. These revolving black holes also have a so-called aerosphere, where the black hole's rotation entangles space and time. The aerosphere is the region outside a curved black hole's outer event horizon, where objects are compelled to rotate with the black hole. Theoretically, energy can be extracted from the black hole within the aerosphere. The Kerr metric, which has been used since the 1960s to comprehend the dynamics of accretion disks, jet formations, and other high-energy phenomena surrounding black holes, demonstrates that the behavior and structure of black holes can also be described and evaluated differently than the researcher Schwarzschild did. Theoretical physics and astrophysics have greatly benefited from K's discoveries, which have significantly altered our current knowledge of gravity. Additional possibilities that Kerr has put forth cast doubt on the existence of singularities and may provide an alternative view on black hole structure. The knowledge of general relativity and the universe's structure has significantly increased as a result of Roy Kerr's theories and discoveries, especially with regard to whirling black holes and the intricate phenomena that surround them. Kerr makes the case that the general relativity assumption of singularities may be incorrect in a very understandable and mathematically sound manner. He clarifies that mathematical calculations indicating singularities do not always imply that these points must exist in reality. Actual physical endpoints are not always indicated by the values utilized in these computations. Even if there are no singularities and a scientist can rationally demonstrate that the assumptions of general relativity do not need to be true for our physics to function, what else is real? How can we solve the universe's mysteries, and will we ever discover the truth? Our research and observations are likely bringing us to the point where we must finally find the unification of the quantum level with the world of physically observable objects. This is what Einstein referred to as the unified field equation, a formula that equally describes the macrocosm and microcosm. We don't know if we will ever be able to physically and mathematically understand everything that the universe truly is, but this formula must exist. Or, to put it another way, there must be a bridge between the two. Think about it. If a physicist wanted to calculate your body, they could use measurements of length and width to describe gravity, your weight, the circulation of your breath, or how you accelerate when you run. It's obvious that physics will never be enough to describe such a complex but completely natural object as your body. Perhaps the universe is similar to your body. Perhaps we have only measured and calculated this one side for far too long, but we have ignored the fact that the universe has dimensions that this scientific discipline cannot. People have long believed that stars, planets, and everything else in the universe are just dead objects. However, for the past 100 years or so, we have realized how dynamic the universe is, and we are now at a point where we must adjust our expectations regarding predictability. The quantum world in particular teaches us that nothing is as it seems. Quanta are the building blocks of the world we see, and they are not static, predictable, or even truly solid matter. Since string theory postulates that the fundamental building blocks of the universe are one-dimension threads, Royer is one of the proponents of loop quantum gravity, which describes spacetime as a network of small, separate building blocks. Both theories have the potential to theoretically unite the subatomic and visible worlds, while general relativity describes gravity and the structure of the universe on large scales, such as planets, stars, and galaxies. Like the other fundamental forces in loop, gravity is described by quantum gravity as a quantized interaction. Despite the potential solutions, we currently only have theories and assumptions rather than concrete explanations or proof. In quantum gravity, gravity is caused by small units, while in string theory, gravity is caused by the oscillations of the threads or strings. In these theories, the force that we know as gravity originates from a particle that scientists call a graviton, but the graviton has not yet been discovered or proven. Work on this is being done at the Large Hadron Collider in Geneva, among other locations. Everywhere we look in physics right now, whether it's at the temporal edge of the universe where the JWST is discovering one impossibility after another at the smallest particles, or even in theoretical physics, the old values are crumbling everywhere, and completely new and expected worlds are opening up. In 2024, scientists discovered that quantum behaves very differently than previously assumed. They can change their behavior very quickly under certain conditions, which means that they exhibit movements and dynamics that are far removed from our familiar Newtonian laws of motion or gravity.